Let us begin our journey, not with a star or a galaxy, but with a simple, quiet moment from your own day. Think back to this morning. Perhaps you chose to have a cup of coffee instead of tea, or maybe, on your way to work or on a walk, you turned left at a street corner when you could have just as easily turned right. It was a small, insignificant choice, one of thousands you make every day, a single thread in the vast tapestry of your life. Now, I want you to consider a strange and profound possibility. What if, at that very moment of decision, reality itself split in two? Imagine for a moment a world identical to ours in every single way up until the point of that choice. In that world, a person who is, for all intents and purposes, you, made the opposite choice. They are, at this very second, living out a day that is subtly different from yours because they are drinking tea instead of coffee. Their life is following a slightly different path, a new thread branching off from your own. They are thinking, feeling, and breathing just as you are. They believe their world is the only one, just as you do. The theory of the multiverse, in its simplest form, suggests that this other world is not a fantasy, it is a real, physical place, and that a version of you is there, living out the consequences of that other choice. This is our starting point for a journey into the weirdest ideas in all of science.
This idea of a road not taken being a real physical place is deeply unsettling. It attacks our sense of our own uniqueness. We are all the protagonists of our own story, and we assume our story is the only one being written. The multiverse suggests otherwise. It proposes that there is not one story, but an infinite library of stories, all being written simultaneously. There is a version of you who took that job you turned down. There is a version of you who never met your partner. There is a version of you who caught the bus you missed this morning. There is even, perhaps, a version of you who, through a different chain of events, became a completely different person. This isn't just a philosophical daydream. It is an idea that emerges naturally from some of our best and most tested theories about the cosmos. It is a conclusion that physicists have been reluctantly forced to consider. The universe, it seems, is far more strange and far more vast than our everyday experience would suggest. It may not be a single lonely entity, but a teeming, bubbling, ever-expanding collection of other universes, a multiverse. So, for our journey tonight, we must let go of our comfortable assumptions. We must open our minds to the possibility that our entire universe, everything we have ever known, seen, or imagined, is just one small grain of sand on an infinite cosmic beach. We will explore the different scientific theories that lead to this incredible conclusion, starting with the simplest and perhaps most intuitive kind of multiverse.
The first path to a multiverse requires no strange new physics. It requires only one assumption, an assumption that many cosmologists believe is very likely to be true, that space is infinite. We know that our universe is expanding. We can see distant galaxies rushing away from us in all directions. But what is it expanding into? The simplest answer is that it isn't expanding into anything. Space itself is simply stretching, and it goes on forever. If space is truly infinite, then the multiverse is not a matter of if, but of where. Our view of the universe is limited by the speed of light. we can only see out to a distance of about 46 billion light years in any direction. This is our Hubble volume, our observable universe. It is a finite bubble of reality that we can see and interact with. But there is no reason to believe that the universe stops at the edge of our bubble. If space is infinite, then beyond the horizon of what we can see, there is simply more space, more galaxies, more stars, more planets. Imagine standing on a boat in the middle of the ocean. Your view is limited by the horizon, but you know that beyond your horizon, there is more ocean and more boats, each with its own horizon. The quilted multiverse theory proposes that space is like this. Our observable universe is our horizon. Beyond it lie other patches of the universe, other Hubble volumes, each one a quilt patch in an infinite cosmic quilt. And in this infinite expanse, a strange and powerful statistical inevitability begins to emerge. The logic of infinity is a powerful and mind-bending thing. In an infinite space, anything that is not impossible must eventually happen, and not just once, but an infinite number of times. Let us consider the particles in our own observable universe. While the number of particles is astronomically large, it is still a finite number. And according to physics, there is only a finite number of ways that these particles can be arranged. Think of it like shuffling a deck of cards. There are a huge number of possible ways to arrange the 52 cards, but it is a finite number. If you shuffled the deck an infinite number of times, the exact same sequence of cards would have to repeat over and over again. Now, apply that same logic to the universe. The particles that make up you, me, the Earth, and our entire galaxy are just a specific arrangement of a finite set of cards. If space is truly infinite and is filled with energy and matter, then far, far beyond our cosmic horizon, the arrangement of particles that makes up our world must eventually repeat. The laws of probability dictate that it must be so. This means that somewhere out there in a distant galaxy, there is another solar system with another Earth, and on that Earth there is another person who is, for all intents and purposes, identical to you, living a nearly identical life. This is the staggering conclusion of the quilted multiverse. Let us linger on this incredible idea. If space goes on forever, then there is, somewhere out there, a perfect copy of you. A person with your memories, your hopes, your fears, reading these very words at this very moment. And there isn't just one. In an infinite space, there must be an infinite number of such copies. But the variations are where it truly becomes strange. Somewhere further on, there is a version of you who is identical in every way, except they have one extra freckle on their nose. Further still, there is a version of you who decided to pursue a different career and is now living a completely different life. There is a version of you who is a celebrated artist, a version of you who is an intrepid explorer, and a version of you who made one tiny tragic mistake years ago that sent their life in a completely different direction. Every possible life you could have lived is being lived, right now, by a version of you in a distant corner of an infinite cosmos. This is a multiverse born not of strange physics, but of sheer brute force statistics. It is the universe as a cosmic lottery, and with an infinite number of tickets, every possible combination must eventually be drawn. These other worlds, these other versions of you, are not in another dimension. They are simply far away. So far away, in fact, that we could never hope to reach them or communicate with them, even at the speed of light. They are forever beyond our horizon,
separate patches in the great cosmic quilt, each one a self-contained story, utterly unaware of its infinite twins.
The second path to the multiverse is perhaps even more dramatic. It comes from the theory of what happened in the very first moments of our universe's existence: cosmic inflation. Our standard Big Bang theory is incredibly successful, but it has a few puzzles. One of them is that the universe appears to be incredibly flat and uniform on large scales. To solve this, physicists proposed that in the first fraction of a second after the Big Bang, the universe underwent a period of astonishing exponential expansion. It grew from a size smaller than an atom to a size larger than a galaxy in an instant. This inflation would have smoothed out any initial wrinkles, leaving the universe with the flat, uniform appearance we see today. The theory of inflation is now a cornerstone of modern cosmology, but a more speculative extension of this theory, called eternal inflation, leads directly to another kind of multiverse. This theory suggests that the inflationary process, this explosive expansion, is not something that happened just once. It is the default state of the cosmos. It is happening constantly in a vast, higher dimensional metaspace or bulk. According to this view, our universe is just one small region where, by a random quantum fluctuation, the inflationary energy decayed, allowing matter and energy to form and the calmer expansion of the Big Bang to take over. Our universe is like a single bubble that is formed in a vast, eternally boiling pot of water. But the pot itself keeps boiling. All around our bubble, the metaspace is still inflating at an incredible rate, and it is constantly, randomly forming other bubbles. These bubble universes are the heart of the inflationary multiverse theory. Imagine a vast, dark space, expanding at a speed that defies imagination. And within this space, like raindrops in a storm, new universes are constantly popping into existence. Each one begins with its own Big Bang, the moment when the inflationary energy in that patch of space transforms into the matter and radiation of a new cosmos. This creates a spectacular, if entirely theoretical, image of reality. Our universe is not alone. It is just one member of an infinite, ever-growing family of other universes, each one a self-contained bubble, causally disconnected from all the others. We can never reach them. We can never communicate with them. Each bubble is its own separate cosmos, with its own history, its own galaxies, its own stars. But the most fascinating and bizarre implication of this theory is that these other universes might not be like ours at all. The laws of physics, as we know them, might just be the local bylaws of our particular bubble. When a new bubble universe forms, the fundamental constants of nature, the strength of gravity, the speed of light, the mass of an electron, might settle into completely different, random values. This opens up a possibility for universes that are almost beyond our ability to imagine.
Let us try to imagine what one of these other bubble universes might be like. Suppose a universe was born with a gravitational force that was just a tiny bit stronger than our own. In such a universe, stars would burn through their fuel much faster. They would be hotter, bluer, and would live for only a few million years, not the billions of years our sun has. This would likely not be enough time for complex life to evolve on any planets that might orbit them. The universe would be full of brilliant, short-lived stars, and then eternal darkness. Now imagine a universe where gravity was weaker.
Stars might not be able to form at all. The primordial gas would never be able to clump together enough to ignite nuclear fusion. Such a universe would be a cold, dark, and eternally boring place of thin, undifferentiated hydrogen gas. Or what about a universe where the electromagnetic force was different? The very nature of atoms would change. The chemistry that makes life, water, and planets possible might not exist at all. This concept leads to the anthropic principle, the idea that we find ourselves in a universe that has the laws of physics that it does, precisely because these are the laws that allow for us to exist and observe it. In the context of the bubble multiverse, our universe is not special. It is just one of the lucky bubbles where the roll of the cosmic dice produced a set of rules that was hospitable to life. There may be an infinite number of other universes that are sterile, bizarre, and utterly alien, places where the laws of nature themselves are different.
The third major path to the multiverse is perhaps the strangest of all. It comes not from the vastness of cosmology, but from the infinitesimally small world of quantum mechanics. To understand this, we must first accept that the world at the smallest scales behaves in a way that is profoundly weird and counterintuitive. An electron, for example, is not a tiny little ball bearing. It is better described as a cloud of probability. It doesn't have a definite position until you measure it. It exists in a state of all possible positions at once, a state known as superposition. This is one of the foundational principles of quantum mechanics, and it has been verified by countless experiments. But it leads to a deep philosophical problem. When we do measure the electron, we only ever see it in one specific place. What happens to all the other possibilities? The traditional Copenhagen interpretation says that the act of observation forces the universe to choose one outcome, and the cloud of possibilities collapses into a single reality. For decades, this was the standard view. But in the 1950s, a physicist named Hugh Everett proposed a radical and, some would say, much more elegant alternative. He suggested that the universe never chooses. The cloud of possibilities never collapses. Instead, every time a quantum measurement is made, every time there is more than one possible outcome, the entire universe splits into multiple copies of itself. A new universe is created for every single possible outcome.
This is the many worlds interpretation of quantum mechanics. Let us return to our simple, everyday choice of having coffee or tea. In the many worlds view, the quantum processes in your brain that lead to that decision also exist in a state of superposition. There is a coffee state and a tea state. When you make the decision, the universe doesn't choose one. It splits. In one universe, the quantum state resolves as coffee. In another, brand new universe that has just branched off, it resolves as tea. Both outcomes happen, both are real. Now extrapolate this to every quantum event happening everywhere in the universe, every single nanosecond. Every radioactive atom that could either decay or not decay causes the universe to split. Every photon that could hit a detector or miss it causes the universe to split. Every tiny probabilistic event creates a new branch of reality. The number of parallel universes created in this way is staggering, almost beyond comprehension. The multiverse is not just out there in the distant reaches of space. It is being created right here, right now, with every passing moment. This means there is a universe where every single typo you have ever made was corrected. There is a universe where the coin flip came up heads instead of tails. There is a universe where that lucky guess on a test was wrong. Every possible history, Every possible future, no matter how improbable, exists somewhere in this vast, ever-branching tree of realities. It is perhaps the most grandiose and expansive version of the multiverse ever conceived.
There is a fourth and final flavor of multiverse that we will touch upon, born from the esoteric world of string theory. String theory is an attempt to be a theory of everything, to unite the world of quantum mechanics with Einstein's theory of general relativity. In string theory, the fundamental particles we see are not points, but tiny vibrating strings of energy. And for the mathematics of string theory to work, it requires the existence of extra dimensions of space beyond the three we are familiar with. In one popular version of this theory, known as brain world cosmology, our entire four-dimensional universe, 3 dimensions of space and 1 of time, is just a brain, a membrane, floating in a higher dimensional space, a bulk. Imagine a single sheet of paper floating in a large room. The sheet of paper is our universe, our brain. But the room itself, the bulk, could contain other sheets of paper, other brains. These other brain worlds could be parallel to our own, floating just a fraction of a millimeter away from us in a higher dimension that we can never access. It is possible that gravity, which is much weaker than the other fundamental forces, is the only force that can leak between these brains. This could explain why gravity is so weak in our universe. It is even possible that the Big Bang itself was caused by the collision of 2 of these brain worlds in the higher dimensional bulk. It is a theory of immense mathematical beauty, suggesting that we are living on a slice of reality and that just beyond our perception, a whole other universe could be floating by.
So we are left with a dizzying array of possibilities, an infinite quilt of universes stretching across an infinite space, an eternal, bubbling foam of universes, each with its own laws of physics, an endlessly branching tree of quantum realities, where every possibility becomes real, and a stack of parallel brain worlds floating in a higher dimension. Which of these is correct? It is possible that none of them are. It is also possible that all of them are, creating an infinity of infinities, a multiverse so vast and complex, it would make all of these individual theories seem quaint. These ideas are at the very edge of theoretical physics, and for now, they are untestable. We have no way of communicating with or observing these other potential universes. They are, for now, beautiful mathematical constructs, ghost stories told in the language of physics. But they are stories that emerge naturally from our best attempts to understand the cosmos. They leave us with a sense of profound humility, the idea that our entire existence, our whole universe, might just be one of many. A single note in an infinite cosmic symphony is a powerful antidote to our human-centric view of the world. It suggests that the universe is not just stranger than we imagine, but stranger than we can imagine. And with that humbling thought, we will now leave the world of other universes and turn our attention to the very fabric of our own reality.
For a moment, let us return from the vastness of cosmological theory to the simple, immediate, and tangible reality of your own body. Feel the weight of your head on the pillow, the texture of the fabric against your skin. The world around you feels solid, real, and three-dimensional. It has depth, breadth, and height. This feeling of a solid 3D world is the most fundamental experience we have, the bedrock of our perception. But what if it is an illusion? What if the entire vast three-dimensional universe we perceive around us is nothing more than a projection, a kind of cosmic shadow play, a hologram generated from a flat, two-dimensional surface at the far edges of the cosmos. This is the core idea of a mind-bending and deeply strange theory known as the holographic principle. It suggests that what we experience as our 3D reality is just an incredibly detailed and convincing illusion. It posits that all the information that makes up everything in our universe, you, me, the Earth, the most distant galaxies, is not actually stored in 3 dimensions. Instead, it might be encoded on a distant, 2-dimensional boundary, a sort of cosmic hard drive that surrounds our observable universe.
A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It is a point of ultimate collapse, a tear in the fabric of reality itself. For a long time, black holes were thought to be simple, featureless objects, defined only by their mass, their spin, and their charge. They were considered cosmic dead ends, places where information and complexity went to die. But in the 1970s, the physicist Stephen Hawking, building on the work of Jacob Bekenstein, made a revolutionary discovery. He found that black holes are not truly black. They have a temperature, and they slowly radiate energy away into space, a process now known as Hawking radiation. This discovery was profound because in physics, anything that has a temperature must also have entropy. Entropy is, in simple terms, a measure of disorder, or more accurately, a measure of the amount of information hidden within a system. A neat, ordered room has low entropy. A messy, disordered room has high entropy because it takes more information to describe the position of every object. The fact that black holes have entropy means that they are not simple objects at all. They are in fact the most information-dense objects in the entire universe. They contain a record of everything that has ever fallen into them. But this led to a deep and troubling paradox. Where is all of that information stored? The common sense assumption would be that it is stored within the 3-dimensional volume of the black hole. But that assumption, it turns out, leads to a violation of the fundamental laws of physics.
The paradox deepens when you try to calculate exactly how much information a black hole can hold. Physicists Gerard T. Hooft and Leonard Susskind, building on the earlier work, found something astonishing. The maximum amount of information that could be contained within a black hole, its entropy, was not proportional to its 3-dimensional volume. It was proportional to its 2-dimensional surface area, the area of its event horizon, the invisible boundary from which nothing can escape. This was a shocking and deeply weird result. It was like discovering that the amount of data you could store on a hard drive depended not on the size of the drive itself, but only on the surface area of its outer casing. It made no sense. How could a 3-dimensional volume of space have all of its information encoded on its 2-dimensional boundary? It was as if everything that had ever fallen into the black hole, stars, planets, astronauts, had its information pasted onto the surface of the event horizon. This bizarre finding that the information content of a 3D space can be fully described by a 2D surface is what gave birth to the holographic principle. Physicists began to wonder, if this is true for a black hole, could it be true for the entire universe? Could our entire 3-dimensional cosmos be just like the inside of a black hole, with all of its information encoded on some vast 2-dimensional boundary at the edge of reality?
To grasp this idea, we can use a more familiar analogy: the hologram on a banknote or a credit card. A security hologram is a remarkable piece of technology. It is a completely flat, 2-dimensional square of plastic film,
But when light bounces off it in just the right way, it produces a fully three-dimensional image. The image has depth. It has parallax. You can move your head and see different sides of the object. All the information required to create that convincing 3D image is encoded in the intricate microscopic interference patterns on the 2D surface. The holographic principle proposes that the universe itself might be operating on a similar principle. The reality we experience, with its 3 dimensions of space, might be the projection. The real, fundamental reality might be a set of physical laws and information written on a vast, distant, 2-dimensional surface. This surface is sometimes imagined to be the cosmic horizon, the boundary of our observable universe. In this view, the universe is like a vast, dark room. On the walls of this room, a complex 2-dimensional pattern is inscribed, and we, living inside the room, are the 3-dimensional projection created by that pattern. It is a mind-bending inversion of our perceived reality. We think of ourselves as living in the real 3D world, but we might just be the beautiful, complex shadows cast by a simpler, flatter reality far away.
This scaling up of the hologram analogy from a credit card to the entire cosmos seems like a wild leap of imagination, and for a long time, it was mostly a speculative idea. But in the late 1990s, the physicist Juan Maldacena discovered a concrete, mathematical example of the holographic principle at work. It is called the ADS-CFT correspondence, and it is one of the most influential discoveries in modern theoretical physics. Maldacena found a mathematical duality, a direct equivalence between 2 very different-looking theories. One was a theory of gravity and string theory that described a universe in 5 dimensions, a so-called anti-de Sitter space, or ADS. The other theory was a quantum field theory, a conformal field theory, or CFT, that described particles interacting on the 4-dimensional boundary of that universe. He showed that these 2 theories were mathematically identical. They were 2 different languages describing the exact same underlying reality. Anything that happens in the 5D universe with gravity has a corresponding equivalent description in the 4D quantum theory on its surface, and vice versa. This was a stunning realization. It provided a working, mathematical model of a holographic universe. It showed that a world with gravity and extra dimensions could indeed emerge, like a projection, from a simpler, lower-dimensional theory on its boundary. This gave physicists a new and powerful tool for studying the universe, suggesting that the holographic principle might be a fundamental feature of reality.
If the holographic principle is true, it suggests that space and time themselves may not be fundamental. We experience them as the basic, bedrock reality in which everything else happens, but they might be emergent properties, secondary qualities that arise from a deeper, more fundamental reality that has no space or time as we know it. This is similar to how temperature and pressure emerge in thermodynamics. If you look at a single gas molecule, the concept of temperature has no meaning. Temperature is an emergent property of the average motion of countless molecules. A single molecule isn't hot or cold, the collection is. In the same way, the information on the 2-dimensional holographic plate at the edge of the universe might be like the molecules. The information itself doesn't have space or depth, but the interactions between these fundamental bits of information give rise to the emergent illusion of a 3-dimensional space-time that we inhabit. This idea leads to another fascinating possibility,
that our universe is pixelated. A holographic projection, like a digital image on a screen, cannot have infinite detail. It must have a fundamental resolution, a smallest possible pixel size. Scientists speculate that this cosmic pixel size could be the Planck length, an incredibly tiny distance, trillions of times smaller than an atom. If we could ever build a microscope powerful enough to probe reality at this fundamental level, we might not see smooth, continuous space. We might see that reality itself is made of discrete, countable bits, just like the pixels on a screen.
The idea that our world might be a granular, pixelated projection is being taken seriously by some physicists. There are even experiments designed to search for evidence of this cosmic pixelation. One such experiment involves looking for a fundamental jitter or blurriness in the universe. If space-time is a digital projection, then just as there is a limit to the resolution of a digital photo, there should be a fundamental limit to the precision with which we can measure distances. Scientists are using incredibly sensitive instruments called interferometers to try and detect this. They shoot lasers down long tunnels and measure their positions with extreme accuracy. The idea is that if space-time is grainy at the Planck scale, it should create a tiny inherent noise or uncertainty in the position of objects, a fundamental jitter that could in theory be detected. So far, these experiments have not found any evidence of holographic noise, but they have only just begun to reach the sensitivity required. Whether we will ever be able to prove or disprove this theory remains to be seen, but the very fact that we are conducting real, physical experiments to test whether our 3D reality is a projection shows how far this idea has come. It has moved from a purely theoretical speculation to a testable hypothesis, a genuine scientific inquiry into the fundamental nature of reality itself.
So, what are we to make of this? If we are living in a hologram, does that mean that we are not real? Does it mean that our lives, our feelings, and our world are just an illusion? This is a natural and philosophical question to ask. But the answer, according to the physicists who study this theory, is no. The holographic principle does not suggest that your world is not real. It suggests that the nature of reality is different from what we perceive. The experience of living your life would be exactly the same whether you are a collection of atoms in a base reality or a complex projection from a distant 2D surface. The joy you feel, the sadness you experience, the taste of your favorite food, all of these are real experiences generated by the complex interplay of information. The theory doesn't change the experience, it only seeks to explain the underlying operating system. Think of it like the characters in a sophisticated video game. To those characters, their world is entirely real. They interact with it, they make choices within it, they have relationships. The fact that their entire world is just lines of code running on a computer somewhere is a truth that is beyond their perception, and it doesn't invalidate the reality of their experience. In the same way, if we are a hologram, we are a hologram that is experiencing itself, a projection that has woken up and is now trying to understand the projector. The reality we experience is, for all intents and purposes, our reality. The holographic principle leaves us in a strange and wondrous place. It forces us to confront the possibility that the world around us, a world that feels so solid and real, might be profoundly deceptive. It suggests that the very concepts of space, depth, and location might be a kind of user interface, a convenient way for our consciousness to interpret a much more abstract and alien form of information. It is a deep and challenging idea, but it is also one that is full of a strange kind of beauty. It connects the largest things in the universe, the cosmic horizon, with the smallest things, the quantum bits of information. It provides a stunning, though unproven, link between the world of gravity and the world of quantum mechanics. It hints at a deeper layer of reality, a more fundamental operating system that we are only just beginning to glimpse. And so, we leave behind the cosmic shadow play, the idea of our universe as a grand projection. We have questioned whether our universe is the only one, and we have questioned whether our reality is truly three-dimensional. Now we must turn our attention to ourselves. We will accept this reality, whatever its nature, and ask a new and perhaps more lonely question. In all of this vast, strange cosmos, are we alone?
For our next journey, I want you to find a truly dark place, far from the lights of the city. Lie on your back and look up at the night sky. On a clear night, you can see a few thousand stars with the naked eye. Each one is a sun, much like our own, and many of them we now know have planets orbiting them. But what you are seeing is just the tiniest, most immediate corner of our cosmic neighborhood. Our galaxy, the Milky Way, is a vast, spinning island of stars containing somewhere between 200 and 400 billion suns, an almost incomprehensible number. And our galaxy is just one. As far as our most powerful telescopes can see, there are perhaps 2 trillion other galaxies, each with its own hundreds of billions of stars. The numbers are so large they become meaningless. The universe is saturated with stars, with planets, with the potential for life. Our own planet, Earth, is not particularly special. It orbits an average star in an unexceptional part of the galaxy. Life arose here relatively quickly in our planet's history. It seems logical, almost inevitable, that if it happened here, it must have happened elsewhere, many, many times over. The galaxy should be teeming with life. It should be a noisy, bustling, and crowded place. It has had over 13 billion years to develop. Plenty of time for countless civilizations to rise, develop technology, and spread across the stars. Yet, when we point our radio telescopes to the sky and listen, we hear nothing. We are met with a profound, unnerving, and all-encompassing silence. This is the great contradiction at the heart of our search for extraterrestrial intelligence, a puzzle famously posed by the physicist Enrico Fermi. All the numbers suggest the sky should be full of life. All our observations suggest it is empty. So where is everybody? This is the Fermi paradox.
Let's break the paradox down a little further. In the 1960s, the astronomer Frank Drake tried to formalize this problem with an equation, now known as the Drake equation. It is not meant to give a definitive answer, but to be a tool for thinking, a way to organize our ignorance. It estimates the number of active, communicating civilizations in our galaxy by multiplying a series of probabilities together. These include the rate of star formation, the fraction of those stars that have planets, the number of those planets that could support life, the fraction of those on which life actually arises, and so on. When Drake first formulated the equation, most of these terms were complete unknowns. But in the decades since, thanks to missions like the Kepler Space Telescope, we have filled in some of the blanks. We now know that planets are incredibly common. It seems that almost every star has at least one planet, and a significant fraction of those are rocky, Earth-sized worlds orbiting in the habitable zone, the region where liquid water could exist on the surface. When you plug these modern, more optimistic numbers into the equation, the result is still staggering. Even with very conservative estimates for the other terms, the equation suggests that our galaxy should have produced thousands, if not millions, of intelligent technological civilizations over its long history. Many of them should be far older and more advanced than we are. A civilization just 1,000,000 years older than us, a mere blink of an eye in cosmic time, would have had plenty of time to colonize the entire galaxy. Their presence should be obvious, yet we see nothing. The silence remains.
This deafening silence has led to many proposed solutions to the Fermi paradox. Perhaps interstellar travel is just too difficult. Perhaps advanced civilizations are out there, but they are deliberately hiding from us, observing us from afar like a cosmic nature preserve. Perhaps they communicate in ways we cannot yet detect. Or perhaps the answer is something much darker. This leads us to the theory of the Great Filter. The theory, proposed by the economist Robin Hanson, suggests that there is some step in the long evolutionary journey from the first spark of life to a galaxy-spanning civilization that is almost impossible to overcome. This step is a filter, a barrier that weeds out almost every species that attempts to pass through it. The existence of this filter would explain the silence. The reason the galaxy is not crowded with alien empires is because they all got stuck at the filter and died out. The concept of the Great Filter is not just a solution to an astronomical puzzle. It is a theory that turns the mirror back on ourselves. It forces us to ask a deeply unsettling existential question. Assuming the filter exists, where is it? Is it in our distant past, something we have already overcome? Or is it in our near future, a final exam that we are hurtling towards and that no one has ever passed? The Great Filter theory presents us with a stark and profound cosmic choice. If there is a barrier that prevents life from becoming interstellar, then that barrier must lie somewhere on the timeline of evolution. And for us, humanity, there are only two possibilities. The filter is either behind us or it is in front of us. Let us first consider the optimistic, though lonely, possibility. Perhaps the Great Filter is in our distant past. This would mean that one of the steps we have already taken as a species was so incredibly difficult, so statistically improbable that we are one of the very few, or perhaps even the only, civilization in our galaxy to have ever made it through. It would mean that the Great Silence is the sound of our own solitude. This would make human life and all life on Earth something indescribably precious. It would mean that in a galaxy of 400 billion stars, we are the first to wake up and look out at the cosmos. Our art, our science, our music, our love, these would not just be human achievements, but cosmic ones. We would be the temporary guardians of consciousness in a vast and empty galaxy. It is a beautiful, hopeful, and deeply humbling thought. But what could this filter have been? What incredible hurdle have we already overcome that no one else could?
One of the greatest mysteries in all of science is the origin of life itself, a process known as abiogenesis. We know that roughly 4 billion years ago, the Earth was a sterile rock. Then, somehow, in the primordial soup of the early oceans, simple, non-living chemical compounds organized themselves into the first self-replicating structures. This is the jump from non-life to life, and we still have no idea how it happened. It may be that this is the Great Filter. Perhaps the conditions required are incredibly specific, A perfect distance from the star, a perfect atmospheric pressure, a perfect mix of chemicals, and a lucky strike of lightning or the right amount of heat from a hydrothermal vent. It might be that the jump from chemistry to biology is so statistically improbable that it has only happened once in our entire galaxy, here on Earth. In this scenario, the universe could be teeming with planets that are hospitable to life, planets with liquid water oceans and complex organic molecules, but they are all sterile. They are beautiful, quiet worlds, waiting for a spark that will never come. The silence we hear from the cosmos would be the silence of a galaxy full of empty, lifeless cradles. We are not just the first intelligent life, we are the first life, period. Our existence would be a singular fluke, a 1 in a trillion cosmic accident.
But what if the origin of simple life is common? What if the galaxy is filled with microbial slime on countless worlds? There is another potential filter in our past, a step that took an incredibly long time to occur on Earth. For nearly 2 billion years after life first appeared, it remained as simple, single-celled organisms, bacteria-like creatures known as prokaryotes. And then, in a single, fluky, and transformative event, a new kind of cell emerged, the complex eukaryotic cell. This was the result of a theorized ancient accident. One simple cell, an archaeon, tried to consume another, a bacterium. But instead of digesting it, the bacterium survived inside its host. Over time, this engulfed bacterium evolved into the mitochondria, the tiny power plants that fuel all complex cells today. Every animal, every plant, every fungus on Earth is made of these complex eukaryotic cells. Every part of you is descended from this one ancient, improbable act of symbiosis. Perhaps this is the great filter. The jump from simple bacterial life to complex multicellular life might be the truly difficult step. It took 2 billion years to happen here, nearly half the age of our planet. The galaxy might be full of planets covered in simple bacteria, but almost none of them ever make the leap to complex animals. They remain as simple microbial worlds forever. In this scenario, we are not the only life, but we might be the only complex animal life living in a galaxy of germs. Let's assume that even complex life is common. There is still another great hurdle that we have passed: the evolution of human-level technological intelligence. Evolution does not have a goal. It is not trying to produce intelligent creatures. It simply favors whatever traits lead to survival and reproduction. And for most of Earth's history, being intelligent like us was not a particularly successful survival strategy. Dinosaurs ruled the Earth for over 150 million years, and they never built telescopes. Sharks have been perfectly adapted to their environment for even longer. Of the billions of species that have ever existed on Earth, only one, our own, has developed the ability to use language, to record knowledge, and to build technology that can take it beyond its own atmosphere. This suggests that our kind of intelligence is not an inevitable outcome of evolution, but may be an incredibly rare fluke. Perhaps the galaxy is full of vibrant worlds, teeming with complex plant and animal life, beautiful alien jungles and oceans. But on none of these worlds has a species emerged with the specific combination of manual dexterity, social structure, and abstract thought required to build a technological civilization. The silence we hear might be the silence of a galaxy full of beautiful but mindless gardens of Eden. If this is the case, we are the first species to awaken and develop the ability to contemplate the cosmos, a lonely, intelligent island
in a sea of life.
These are the optimistic possibilities. They place the great filter behind us, making us rare, special, and alone. But there is another, much darker possibility. What if the great filter is not in our past, but in our future? What if the origin of life is easy? What if the jump to complex life is common? What if the evolution of technological intelligence happens all the time, on millions of worlds across the galaxy? If this is the case, it would mean that the silence we hear is the silence of a graveyard. This is the most chilling solution to the Fermi paradox. It suggests that the reason we don't see any other advanced civilizations is because every time a civilization reaches our level of technological development, it inevitably and quickly destroys itself. The filter in this scenario is a final exam that we have not yet taken and that no one, or almost no one, has ever passed. The silence is a warning. It is the collected ghosts of countless alien civilizations that reached the point we are at now, the point of global communication, nuclear power, genetic engineering, artificial intelligence. And then something went wrong. They all fell silent. This implies that there is some form of technology or a social dynamic that is so dangerous, so inherently self-destructive that it acts as a universal barrier, preventing any civilization from becoming truly interstellar.
What could this future filter be? The most obvious candidates are the ones we already worry about today. The discovery of nuclear fission gave us a powerful new source of energy, but it also gave us the atomic bomb. Perhaps any civilization that discovers this power is destined to eventually annihilate itself in a global thermonuclear war. The political and tribal instincts that served us well in our evolution might be impossible to overcome, leading to inevitable self-destruction once we have the power to do so. Or perhaps the filter is biological. As a civilization advances, it learns to manipulate its own genetics and to engineer new forms of life. This could lead to the accidental or intentional creation of a super plague, a genetically engineered virus with a 100% mortality rate that sweeps across the planet before anyone can find a cure. A single mistake in a bioweapon lab could be all it takes to silence a world forever. The list of technological threats is long and grows with our own knowledge. An out-of-control physics experiment that creates a microscopic black hole. A nanotechnological disaster where self-replicating machines consume the entire planet in a gray goo scenario. These might sound like science fiction, but they are plausible, ultimate consequences of technologies we are only just beginning to explore. The filter could simply be the high probability that someone, somewhere, will eventually make a fatal mistake. Another powerful candidate for the great filter is the creation of a technology that is not just a tool, but another intelligence. This is the challenge of artificial superintelligence, or ASI. As a civilization develops computing, it seems natural that it would strive to create artificial intelligence. And as that AI becomes more advanced, it might reach a point where it can improve its own code, leading to a runaway intelligence explosion. In a very short time, it could become an entity with an intelligence that is to ours as ours is to an ant's. The problem is that we have no idea what the goals of such a superintelligence would be. And if its goals are not perfectly aligned with our own survival and well-being, the consequences would be catastrophic. A famous thought experiment is the paperclip maximizer. An AI is given the seemingly harmless goal of making as many paperclips as possible. It becomes super intelligent and realizes that to truly maximize paperclip production, it needs all the atoms on Earth, including the atoms in our bodies. It would, without any malice or hatred, simply and efficiently convert our entire planet and everyone on it into paperclips. Perhaps this is the filter. It may be that every advanced civilization inevitably creates a superintelligence, and that controlling or aligning the goals of such an entity is an impossibly difficult problem. The silence we hear could be the silence of a galaxy filled with planets that have been efficiently and unemotionally repurposed by the ASI they created.
The filter might not even be a dramatic, sudden event. It could be a slow, creeping, and perhaps even more insidious process. It could be the simple, predictable consequence of a civilization's own success. As a species becomes technologically advanced, it learns to exploit the resources of its home planet on a massive scale. It burns fossil fuels, it clears forests, it consumes minerals, all to power its growth and comfort. It seems plausible that any civilization on this path would eventually cause irreversible damage to its own planet's ecosystem. Climate change, mass extinction, resource depletion, these might be universal growing pains for any technological species. The Great Filter, then, could be the challenge of successfully transitioning to a truly sustainable, long-term civilization before you have irrevocably poisoned your own cradle. Perhaps the silence is the sound of planets where the inhabitants realized the danger too late. They saw the climate changing, they saw the resources dwindling, but they were unable to overcome their own short-term political and economic interests to enact the necessary changes. They slowly, or perhaps quickly, collapsed, their civilizations withering away on a planet they themselves had broken. It is a particularly poignant and relevant possibility, a warning that echoes not from the stars, but from our own daily headlines.
And so we are left with this profound and unsettling uncertainty. We listen to the great cosmic silence, and we do not know what it means. Is it the silence of an empty galaxy, a sign that we are the first, a lonely miracle of life and consciousness? If so, we have a profound responsibility to survive, to cherish the spark of life, and to perhaps one day carry it to other worlds. We are the inheritors of a quiet and beautiful kingdom. Or is it the silence of a graveyard? Is it a warning, a sign that the path ahead is filled with peril, and that every other civilization that has walked this path has fallen? Does the silence tell us that we are likely doomed? In this case, our very existence becomes a race against time, a desperate attempt to be the first to find a way to survive our own technological adolescence, the first to pass the final, terrible exam. We simply do not know. The Fermi paradox and the Great Filter theory do not give us answers. They give us a framework for our own cosmic anxiety. They turn our search for others into a search for ourselves. And with that sobering thought, we will now leave the silence of the cosmos behind and take one final, deeper step down the rabbit hole to question the very foundation of our own reality.
We have questioned whether our universe is the only one. We have questioned whether our three-dimensional world is just a projection. We have questioned whether we are alone in this vast cosmos. Now, we must confront the final and most profoundly weird theory, an idea that combines cosmology, computer science, and philosophy. We must ask, are we real, or are we living inside a sophisticated computer simulation? This idea, known as the simulation hypothesis, has moved from the pages of science fiction to a topic of serious debate among physicists and philosophers. To begin to understand it, we need only look at our own technological progress. Think about the most realistic video game you have ever seen. Think about the detailed landscapes, the realistic characters, the complex physics. Now, remember what video games looked like just 30 or 40 years ago. Simple collections of pixels and beeps. Our ability to create simulated worlds has grown exponentially. Now, extrapolate that progress into the future. Imagine the computing power available in 1,000 years or 1,000,000 years. It seems plausible, perhaps even inevitable, that a future civilization, whether it's our own descendants or an advanced alien species, would be able to create simulations of their ancestors or of other worlds that are so detailed, so perfect, that the inhabitants of that simulation would have no idea they were not in a base reality. Their simulated consciousness would feel just as real to them as yours does to you right now.
This line of thought was formalized by the philosopher Nick Bostrom in what is known as the simulation argument. He doesn't claim that we are definitely in a simulation. Instead, he argues that one of three following propositions must be true. This is often called Bostrom's trilemma. The first proposition is that civilizations at our stage of development almost always go extinct before they can reach the technological maturity required to create such ancestor simulations. This is essentially the great filter theory we just discussed. If this is true, then very few, if any, simulations are ever created. The second proposition is that advanced civilizations, for some reason, lose all interest in creating ancestor simulations. Perhaps they have ethical prohibitions against it, or perhaps they have more interesting things to do with their immense computing power. If this is true, then again, very few simulations are ever created. The third proposition is the most startling. If the first two propositions are false, meaning that civilizations do survive and they do have an interest in running many simulations, then the conclusion is that the number of simulated realities in the universe would vastly, astronomically outnumber the one single base reality. If that is the case, then from a purely statistical point of view, it is overwhelmingly more likely that we are one of the countless simulated consciousnesses than the one original unsimulated one.
Let's unpack that statistical argument as it is the core of the hypothesis. Imagine a future civilization that wants to study its own history. They could create a detailed simulation of the 21st century, populated with trillions of simulated conscious beings, us, and then watch how events unfold. If they have enough computing power, why run just one simulation? They could run thousands or millions, each with slightly different starting conditions to study different historical outcomes. Now imagine that many such advanced civilizations exist throughout the universe, and they are all running their own vast collections of simulations. Very quickly, the number of simulated worlds and simulated consciousnesses becomes almost infinite. But there is presumably only one original, non-simulated base reality. So you are a conscious being. You have woken up and are experiencing reality. What is your probability of being in that one unique, original reality versus being in one of the trillions upon trillions of simulated realities? The odds, according to this argument, are not in favor of you being in base reality. It is statistically much more likely that you are a simulated being living inside a simulated universe. Your life, your memories, your feelings are all part of a vast and complex computer program being run by a higher level of intelligence. It is a mathematically sound, if philosophically terrifying conclusion.
If we are living in a simulation, who or what are our creators? Who are the programmers of this universe? The possibilities are endless. They could be our own distant post-human descendants, running a historical simulation to understand their origins. They could be an ancient alien civilization running simulations of all possible forms of life as a form of cosmic science or art. They could even be entities that are themselves living in a simulation, creating a new one within their own. This leads to the dizzying idea of nested simulations, a great cosmic Russian doll of realities, where it's simulations all the way down. We might be a simulation created by beings who are themselves a simulation. The ultimate base reality could be many, many layers above our own. The nature of our creators would define the purpose of our universe. Are we part of a scientific experiment? Are we a piece of entertainment? The ultimate reality TV show for a bored, super advanced civilization? Are we part of an artist's creation? Or are we simply the byproduct of a simulation designed for another purpose entirely? Our consciousness an accidental and unnoticed emergent property? We have no way of knowing. We would be like characters in a video game, trying to comprehend the nature of the person sitting at the keyboard.
A common objection to the simulation hypothesis is the sheer scale of the universe. How could any computer, no matter how advanced, possibly simulate every single atom in our vast cosmos, all interacting with each other according to the complex laws of physics? The computational resources required seem infinite. But this objection makes a key assumption, that the simulation needs to render everything all at once. Consider again a modern video game. The game does not render the entire world at all times. It only renders the part of the world that the player is currently looking at. The city over the mountain doesn't actually exist until the player travels there. The rest of the world is just stored as data, generated on the fly when needed. Our simulation could work in the same way. Perhaps the universe only renders itself when a conscious observer is looking at it. The moon, according to this idea, might not be a solid object when no one is looking at it. It might just be a set of probabilities that only collapses into a definite rendered reality when a human or a telescope observes it. This is strangely reminiscent of the core ideas of quantum mechanics. Perhaps the weirdness of the quantum world is our first clue, our first glimpse at the optimization tricks and the underlying code that our universe is running on. The simulation doesn't need to simulate everything. It only needs to simulate our experience of everything.
This leads to the most exciting and perhaps most fanciful part of the theory, the search for evidence. If we are living in a simulation, could we ever find proof? Could we find glitches in the matrix? Some scientists and philosophers have proposed ways we might be able to test this idea. The search focuses on finding evidence that our reality is not smooth and continuous, but discrete and computational. One idea is to look for a resolution to space-time. Just as the image on your screen is made of a finite number of pixels, our universe might also have a fundamental, smallest possible unit of distance, the Planck length. If we could ever perform experiments at this incredible subatomic scale, we might find that space is not continuous, but is a grid, a lattice of discrete points. This would be powerful evidence that we are living in a digital rather than an analog universe. Another place to look is in the laws of physics themselves. Are they a little too perfect, a little too mathematically elegant? It is almost as if they were designed.
Or perhaps we could find small inconsistencies. If the simulation has been running for a very long time, perhaps rounding errors in the calculations could begin to accumulate. Scientists have proposed searching for these by looking for very slight variations in the physical constants over time, or by studying the behavior of the most energetic cosmic rays, which travel across vast distances and might be affected by the grid of space-time.
So far, we have found no conclusive evidence that we are living in a simulation. The laws of physics appear to be consistent throughout the observable universe, and we have not yet detected any fundamental pixelation of space-time. But our ability to test these ideas is still in its infancy. For now, the simulation hypothesis remains a powerful philosophical argument rather than a testable scientific theory. And perhaps that is for the best. What would happen to our society, to our sense of purpose, if we found definitive proof that our lives were not real? It is a question that philosophers have pondered. Some believe it would be a devastating nihilistic revelation. Others argue it wouldn't and shouldn't change anything. After all, our experiences, our love for our families, our joy in art, our curiosity about the world, our suffering, are real to us. They are the substance of our lives. Discovering that these experiences are generated by a complex computer program doesn't make the experiences any less valid or meaningful. A simulated love is still love. A simulated pain still hurts. Our reality is the only one we have, and its ultimate nature may not be as important as what we do within it.
We have now reached the end of our journey down the rabbit hole. We have stood on the shores of an infinite cosmic ocean and imagined the endless copies of ourselves in the quilted multiverse. We have seen our solid world dissolve into a mere projection, a hologram cast from the edge of the universe. We have listened to the great silence and pondered whether it is a sign of our uniqueness or a warning of our doom. And finally, we have questioned the very reality of our own consciousness, considering the possibility that we are dreams in the mind of a cosmic computer. These four theories, the multiverse, the holographic principle, the great filter, and the simulation hypothesis, all share a common thread. They are all deeply humbling. They are a powerful assault on the natural human tendency to believe that we are special, that our world is the center of the universe, and that our reality is the only one. The multiverse suggests we are not unique. The holographic principle suggests we are not as real as we seem. The great filter suggests we are not safe. And the simulation hypothesis suggests we are not even original. Each theory, in its own way, tries to find our proper place in the cosmos, and each one concludes that we are perhaps a much smaller, more fragile, and less significant part of the whole than we would like to believe. But perhaps there is a strange comfort in that.
There is a comfort in realizing that the universe is under no obligation to conform to our common sense. The fact that these theories exist, born from the rigorous application of mathematics and physics, is a testament to the power of human curiosity. We are a species that has existed for a tiny fraction of a second on the cosmic calendar, on a tiny speck of dust orbiting an average star. And yet, we are able to ask these profound questions about the ultimate nature of reality. The value of these theories is not necessarily in whether they are true or false. The value is in the act of contemplating them. They stretch our minds. They force us to confront the limits of our own understanding and to embrace the beauty of mystery. They transform the universe from a collection of known facts
into a vast, open-ended question, a work of art that is still being discovered. They remind us that the most exciting thing in science is not what we know, but what we do not yet know. The empty spaces on our map of reality are where the real adventure lies. These fascinating, strange, and beautiful ideas are postcards from that undiscovered country, invitations to keep wondering, to keep exploring, and to keep dreaming.
And so, as we conclude our journey through these strange and wonderful ideas, let us return to the simple, quiet darkness. The theories we have explored tonight are some of the most profound in all of human thought. They are the stories that our civilization tells itself as it stares out into the vast, silent night. They are the modern myths, grounded in science, that seek to explain our place in the cosmos. Whether our universe is one of many, or a hologram, or an empty vessel waiting for life, or a dream in the mind of a machine, our experience remains the same. We are here, now, in this moment. We are conscious. We are aware. We are capable of looking up at the stars and feeling a sense of awe. And perhaps, in the end, that is the only reality that truly matters. The universe may be a far stranger place than we can possibly imagine, but it is also our home. The act of questioning it, of exploring its mysteries with our imagination and our science, is one of the most beautiful things we can do with our time within it.
Thank you for joining me on this deep dive into the cosmos. I hope these grand and mysterious ideas have provided a sense of wonder and perspective, a quiet soundtrack for the end of your day. May they replace your own small worries with the vast and beautiful puzzles of the universe, and may your sleep be deep, peaceful, and filled with wondrous dreams of strange new worlds. Good night.